The Athabasca Basin in northern Saskatchewan is best known as the world's leading source of high-grade uranium and responsible for about 20% of the world's uranium. On the north shore of Lake Athabasca, the Beaver Lodge domain is situated. Historic work in the area dates back to the 1950s. From 1953 to 1982, 16 deposits were brought into production in the Uranium City area, with a total production of over 70 million pounds of uranium oxide, averaging 0.24%. The grades ranged from 0.18 to 0.43%. Most of the uranium deposits in this region are associated with faults, as the faults provide ample fractured ground for hosting uranium mineralization. The main northeast trending faults in the region are the Black Bay and Boom Lake faults, which form the northwest and southeast boundaries of the Black Bay Shear Zone. The Black Bay Shear Zone is a major structural feature which hosts several past-producing mines, such as the past-producing Leonard and Smitty uranium mines, combined to produce 876,000 pounds of uranium oxide, and to the northeast, the Kazor uranium mine produced approximately 1.4 million pounds with unexplored depth potential. The Black Bay Shear Zone is identified as a magnetic low feature. An airborne electromagnetic, more commonly known as an EM survey, identified a conductor corridor within the Black Bay Shear Zone. EM conductors may reflect structurally reactivated graphitic basement rocks. Electromagnetic conductors mark graphite in the basement rocks, and graphite is key for finding uranium in the Athabasca Basin. Many large uranium deposits are associated with graphite-rich faults, which are thought to have acted as near-ideal traps for triggering deposition of unusually large and high-grade ore zones. And it is precisely in this area that Belmont's Crackingstone Uranium property is situated. The Crackingstone property is only 6 kilometers from Uranium City and is accessible by road year-round. A power line runs through the southwest section of the property. On the property, and on strike with the Black Bay Structural Corridor, are the northeasterly Chance Lake and Boom Lake faults. These faults appear to have been reactivated several times to provide ample fractured ground for hosting the uranium mineralization. There appears an area to the east that a structural feature extends westward unto the Crackingstone property. The intersection points of these northeast faults and east-northeast Crackingstone faults appear to be a selected area for the concentration of uranium mineralization as illustrated at the Cinch uranium mine. A fourth fault, named the Nero Lake Fault, extends from the Black Bay Fault in the east, westerly across the southern portion of the property. Since the early 1950s, numerous uranium occurrences throughout the property have been discovered, mapped, and assayed. In 1958, Mr. E. Cull, who drove a short adit, which is now referred to the number 7 adit, from the base of a trench, which previously returned 15.6% uranium oxide over 1.4 feet. He shipped 11 tons of broken rock to the Laredo mill, which graded 2.3% uranium oxide. In 1959, at the Beck 58 showing, channel sampling returned 0.52 meters of 0.36% uranium oxide. Mr. C. Ejnilika high-graded approximately 46 tons, which graded 0.5% uranium oxide. Also, in 1959, uranium stain was visible at a few places near the Beck 91 showing. A grab sample containing considerable yellow stain, possibly fine disseminated pitchblende, from the Beck 93 showing assayed 12.53% uranium oxide. At the Beck 231 showing channel sampling assayed 2.13% over 0.70 meters, 1.46% over 0.49 meters, and 1.32% uranium oxide over 0.64 meters. At the Beck 102 showing a grab sample assayed 5.2% uranium oxide. In October of 2007, Belmont Resources contracted MPX Geophysics to fly a radiometric survey over its Crackingstone property. A radiometric survey, or as it's also referred to as gamma-ray spectrometry, is a surveying technique that allows the calculation of the heat produced during radioactive decay of uranium, thorium, and potassium within the Earth's surface. Many natural elements have radioactive isotopes, but only uranium, thorium, and potassium decay series produce sufficient energy and intensity to be measured by gamma-ray spectrometry. By applying a filtering process that suppresses the lower-grade uranium of the radiometric survey and highlights the higher-grade uranium, we see some interesting linear anomalous uranium trends that are coincident with the major faults. By overlaying the EM conductors, these trends are further enhanced. And once again, by overlaying the uranium surface mineralization, we see the formation of a number of important, structurally controlled fault, EM conductive mineralized corridors. Strong radioactivity was measured on surface in numerous showings across the property. In uranium exploration, a handheld device called a scintillometer is used to test the radioactivity of rocks. CPS, or counts per second, is a measurement used to determine how radioactive something is. The higher, the better. Greater than 300 CPS on the handheld scintillometer would be considered anomalous. Greater than 10,000 CPS would be considered highly radioactive, and greater than 65,000 CPS would be considered as off-scale. In the southern portion of the Crackingstone property, readings ranged from 3,000 CPS to over 65,000 CPS. Worth noting is that these readings were coincident with EM conductors. In the north, readings ranged from 6,000 CPS to a high of 13,000 CPS. In 2007, Belmont focused its exploration on the intersecting east-west and northeast structure along the Crackingstone Fault, Boom Lake Fault system, especially north of the Crackingstone Fault along the Boom Lake Fault. Samples taken from the number 7 adit returned 6.5, 0.78, 0.40, and 0.28% uranium oxide. A detailed gamma-ray survey carried out in this area identified a large area of high radioactive anomalies coincident with the Boom Lake and Crackingstone fault systems. In March of 2008, Belmont carried out a 20-hole, 3,000-meter diamond drilling program covering an 1,800-meter strike length along the Boom Lake Fault. All of the drill core was mineralized with uranium. Holes C14 and C8 both yielded high assays. Assays in C14 ranged as high as 2.08% uranium oxide over 0.5 meters, and this is part of an interval of 0.9 meters, averaging 1.18% uranium oxide. In addition to the uranium mineralization, drilling also intercepted an extensive amount of hematite across the entire 1.8-kilometer zone. Hematite is an alteration type often associated with uranium, and the occurrence of hematite in alteration zones is an indication of uranium precipitation during the hydrothermal event. The results of the 2008 drilling were very positive, with the interception of uranium mineralization, pegmatites and hematite alteration along the Boom Lake and Crackingstone structural fault zones. Belmont had intended to launch an immediate follow-up drilling program, but the low uranium prices at the time led to limited interest in securing financing for uranium projects. Now, some 17 years later, amid a surge in global interest in uranium, Belmont is revisiting the Crackingstone property with plans to begin drilling 4 primary uranium targets. Belmont has signed an exploration agreement with the YNLR Land and Resource Office. The YNLR manages consultation and engagement on behalf of Athabasca First Nations and the Athabasca municipalities. With the consultation process completed, Belmont is now anticipating to receive the final drilling permit from the Fish, Wildlife Lands Branch Saskatchewan Ministry of Environment before January 2025 month end.